Welcome everyone. We're going to begin Module 12 today. This will be the last module for which you are responsible for the final exam. So we've already been discussing light, and today we're going to look at the wave nature of light and how light can cause interference patterns. It's worth noting that this is not the complete picture of light. If we had time, we would have gotten into Module 13 where we would have discussed the particle nature of light. Light is unique compared to sound in this way that it can be understood through both a wave picture and or a particle picture. But for today, we're just looking at the wave nature, and some of this will be somewhat of a review of what you've learned in 110 about sound waves and how they can produce interference as well. Light is no exception, and just as we had learned last semester, if you have waves that are subject to superposition and their peaks line up and their troughs line up, then what you'll produce is constructive interference. If you have a situation where you have the opposite scenario, a peak lines up with a trough and a trough lines up with a peak, then you'll see that the wave essentially cancels itself out and you will have destructive interference. Oftentimes you might have something in between if it's not quite a perfect alignment in either of these cases. And just as we learned with sound, for this to happen at all, it's for you to have constructive or destructive interference, you need for the waves to have the same frequency so that you can hope that if one peak lines up, then a wavelength later, the peak will also line up. If your wavelengths are different or your frequencies are different, that's not going to happen. So you need for this to be a coherent wave source of a single frequency in order to see this kind of interference pattern. Okay, so the question might be, when do we see light behaving this way? A famous example of this is the Young's two-slit experiment, which took essentially a plane wave coming in and forced it onto an obstruction that only had two small slits onto it. After some distance, then there would be a screen, and what happens then is that the light is forced through these narrow little slits, and just like you would expect from perhaps ripples on a pond, this sort of pattern is produced where you have alternating constructive and destructive interference, so that when you look at the screen there will be bright patches and dark patches alternately produced by this interference pattern. And the brightest patch of all actually lines up with the middle of this obstruction between the two slits. So that might be slightly counterintuitive. Let's see if we can understand why that's the case if we quantify this a little bit further. So when the light passes through the slits, it's going to take on some sort of path length to get from where it came through to the screen. If those path lengths are equal to one another, and it's the same frequency, it's just a single frequency to begin with, then you can hope that all of these peaks will line up and produce a bright constructive interference spot right here, which is often termed a fringe. Now, not just there, though. We saw in the previous slide that there were other bright patches. How do we explain those? Well, as long as the difference in the path length is equal to some integer value of the wavelength, then the peaks will still line up with the peaks and the troughs will still line up with the troughs, and you'll produce constructive interference at a different location. So going by that same rationale, if the difference in the path lengths is half of a wavelength, then you're going to have peaks line up with troughs and produce cancellation or destructive interference, and you'll get these dark patches here. Okay, so another way that we can quantify this is in terms of this angle theta. Now, theta can be best understood as the angle between, if I just draw a straight line across here, which is perpendicular to this interface, and I find where the location, the center of this fringe is, and then I produce a right triangle here, that's the theta. How far off this axis am I? Okay, that's how we measure theta. But through some other geographical reasoning, the details of which I won't go into, you can also make certain approximations and understand this in terms of some other trigonometry on the left-hand side of this picture. So the difference in path length is going to be approximately equal to this, like what you're seeing here, that we can treat this like a right triangle here. Okay, and in that case, the hypotenuse of your right triangle is your distance, and so sine times that is going to be, if you solve it, equal to this equation here for our bright fringes. And as we said, any integer value will do, so I can start with 0. 0 is always going to be the case no matter what my wavelength is. So what that is to say, another way to say that is, no matter what frequency I put through my Young's two-slit experiment, I will still have my first fringe, my 0th order fringe, right directly across from the center of this barrier. Okay, and then the locations of these other fringes will depend on what my wavelength of light is. Okay, but they will just build differently off of this center one, depending on the frequency. On the other hand, the dark fringes are always going to be half integer values, so we can do that by adding a 1/2 in here and then plugging in whatever integers we're interested in. So let's say that I wanted to know where the second order bright fringe was, then my m would be equal to 2 in this equation here. Okay, and likewise, if I wanted to know where the second order dark fringe was, I would plug in 2 here for my m. All right, so the thing is that while this equation can be useful for telling us the location of these bright and dark fringes, it does not necessarily tell us the intensity of the bright fringes. It's worth noting that the brightest of these fringes will occur at the m equal to 0, and that they will get increasingly dimmer as I increase my integer value for m. We won't quantify that, but qualitatively that's good to understand that the center one will be the brightest, and then working outward from the center in either direction, the bright fringes will be less and less bright. Okay, so let's do an example where we apply these principles to a two-slit experiment. Let's imagine that we're given a red beam of light with this frequency, and we are sending it into this experiment that has the two slits located this far apart, and we know how far away the screen is from those slits. What we're interested in knowing for this problem is how high up the screen in this y value will be my third order fringe, third order bright fringe. So we take the equation that we were given on the previous slide, which was sine theta equal to m lambda over d, and in this case, since I'm interested in the third fringe, my m is going to be equal to 3. Now notice that this equation involves lambda, but I've been given a frequency. However, recall that the speed of light is going to be equal to lambda times my frequency. So I can solve for this lambda by dividing this speed of light by the frequency. Okay, so if I do all that and I rearrange my equation and plug in all the values, I should find that this angle theta is less than 1 degree. It's 0.95 degrees. Okay, why do I need to know that? Well, in order to determine this y, I need to know something about this angle theta. And if I think about it geometrically, this is also a right triangle, and this is the opposite and the adjacent side. So y over L is going to be equal to tangent of theta. I can solve that equation like so, plug in the values that I was either given or found, and then I can determine that the distance y is going to be equal to, in this example, 4.4 centimeters. Okay, so that's an example of how you would use this kind of reasoning or these equations for a Young's two-slit problem. The final thing I'm going to point out is that we've emphasized throughout this lecture that the importance of there being only a single frequency so that this light is coherent. But there is such a thing as thin film interference. In thin film interference, what happens is your incident light may not consist of one singular frequency, but if it is refracted through a thin layer and then reflected back up at you, there can be interference patterns that are wavelength dependent, so that you still see these bright and dark fringes, but you see the bright fringe for green, for example, in a different place than where you see red or yellow and so on. And so this is familiar to you if you've ever seen a sort of gasoline spill on a wet pavement. This is an example of thin film interference where it combines these principles of refraction. Remember that refraction is a frequency dependent thing, so we can sort of separate out the different colors and then we can produce this interference pattern. Okay, we have one more lecture left that discusses Module 12 a little bit more, and that will be the end of the material for this semester. Talk to you then.